Yeah, thanks a lot. Thanks to the organizers, and also thanks for the opportunity to present some joint work together with Noe Galis and Thilo Spalger about neural fields. And by now almost traditional field of application for neural fields is spatial working memory. I mean, you probably all know these oculomotor delayed response tasks where a monkey has to fixate a point on a screen, and then there's a cue, and the monkey has to remember the location of this cue of the target during some delay period and answer that. And some experiments already back in the 80s by Funahashi and colleagues showed that neurons in the prefrontal cortex that are tuned to that particular target location show some increased persistent activity, while other neurons that are not tuned to that particular target location remain silent. So this gives rise to some bump activity here shown, like some higher discharge rate, which is very much localized, and other neurons that are not tuned to that location remain sort of silent. So this bump activity, this localized, stationary, persistent activity is kind of pertinent for the spatial working memory tasks. And it has been shown that these bump states, or this bump, starts to wander diffusively during the delay period. And that is sort of consistent with a recall error, mainly at the end of the delay task. So the response is that the monkey cannot properly memorize the cue location, target location perfectly, but it deviates slightly from the actual position here marked by this black cross. And to explain these experimental phenomena, there have been various ways, like very many computational models, and one of the main of the seminal approaches is by Albert Comte, Nicolas Brunel, and Rakic, and Xiao Wang, already 20 years back, where they used a detailed spiking neural network model to describe these observed phenomena. And interestingly, they can get and observe also in their computational model the correct spatial temporal dynamics of this bump activity. They also see that there's finite size fluctuations. A first thing what you can do is use maybe the population vector average that also Vivek explained or introduced in his keynote lecture today. So we can extract more or less the bump center here shown as the black line. So this is one trajectory, and then we can kind of run these simulations over and over again, and also for different network sizes. So that is shown here on the lower left, what Comte and colleagues did. And what they found were that this diffusive wandering of the bump, so this edgy behavior of the bump center, this diffusive wandering is more pronounced in smaller networks and becomes weaker and weaker the larger the networks becomes. One can also sort of quantify this bump diffusion in terms of the variance, and the variance increases linear in time. You see large small networks have sort of a large slope, meaning sort of a strong bump diffusion, whereas larger networks have almost no or very little bump diffusion. One disadvantage of these spiking neural network models is that they are analytically not tractable. So for that reason, stochastic neural field models of this form have been introduced, and by Kilpatrick and Armantrout, and also Breslov and colleagues, they put forward a rigorous mathematical sort of theory or treatment to analyze bump solutions of these stochastic neural field models to also quantify bump diffusion and also the stimulus dependence of the bump. Unfortunately, these stochastic neural fields, they remain heuristic. So they are phenomenological models, and in general, they are like the dynamics of the mean activity of the stochastic neural field models are inconsistent with spiking neuron dynamics, for example, in phase of neural refractoriness. And it's also unclear how we can incorporate finite size fluctuations. So there's like 2 points that I want to highlight here. So one is the dynamics mentioned here by this time constant tau. What is that? And the other point is sort of the character of the noise. So this is the sigma, the noise strength, but also the correlation structure of the noise highlighted in red C. This is unclear. And the goal of my talk now is to derive a neural field model from a finite size spiking neural network model that can actually account for these 2 types, for the dynamics, but also for finite size fluctuations. So in an outline of my talk, I will first introduce the particular neural network model, or the neuron model. These are renewal-type spiking neurons. And first, I also concentrate on a single population in order to show that there are low-dimensional dynamics of the population activity. And after that, in the second part, I will come to many interacting populations of finite size. And then I perform an appropriate spatial continuum limit to derive our neural field model that allows to investigate really these finite size fluctuations in more detail. All right, so starting point are renewal-type spiking neurons. These renewal-type spiking neurons are inherently stochastic because we merely assign a probability for the neuron that elicits a spike within a short time interval of length delta t. So this firing probability here, P, that the neuron J spikes in this time interval, is a conditional probability that depends on some input variable uj. You can think about that as some membrane potential, for instance, and on the h tau. Tau means that is, or the h means that is the time that has elapsed since the last spike of that neuron. Okay, so this firing probability P, or this conditional probability, depends on the so-called hazard rate or intensity rho j, which is fully determined by the time t and also by the h tau j. So this rho can be understood as like a rho of tau j and t. In general, often it's like sort of a function of this membrane potential minus some threshold value, and then the time dependent h, or the age of the neuron. Okay, so we have a look at the membrane potential dynamics. Now this is sort of like a first order dynamics, and we couple neurons recurrently with each other synaptically through delta spike trains. And what I colored here in red is basically the population activity, or the rate A of t, in a fully connected network. Okay, so we just rewrite the equations a little. And now we go to the mean field dynamics. For that, we rewrite uj, so the membrane potential of neuron j, in terms of u of the h tau and time t. This leads to this equation here, so where we had like the total derivative now split into like a temporal part and the h part. And we also introduce the refractory density, P, the corresponding time evolution of the refractory density. So let me explain that a little bit in detail. So very similar to, say, the Fokker-Planck approach, where one typically studies the distribution density of membrane potentials, we now group all those neurons together that have the same age at a particular point in time. So if a neuron spikes, then if a neuron does not spike at particular time t, then its age increases linearly in time. On the other hand, if a neuron spikes, then its age tau is reset to 0, sort of reborn. And the fraction of neurons that have age tau, say we're here in this upper figure where my cursor is. So the fraction of neurons with age tau that spike at a particular moment in time, that is proportional to the hazard rate at time t with that particular h tau. So as shown here in the arrow, that is the part, or that is the fraction of neurons with h tau that spike and get reborn at the next point in time. So this is the sinc term here in this transport equation describing the evolution of the refractory density. And if we average over this right-hand side here, so if we average over all these arrows in this upper plot, then we actually get the population activity A, which is basically the refractory density evaluated at tau equals 0. So mathematically speaking, this is a non-local boundary condition. Okay, so to get more practical, let's start with a homogeneous network of renewal-type spiking neurons and just copy all the important formula again. And as one example, we take the Poisson model with absolute refractoriness. So here down left, I plotted the hazard rate versus the h tau. So it's 0 if the h is less than the absolute refractory period, and then it jumps to some constant value, which depends in turn on the input. We can also calculate the interspike interval density, the ISI density, which would play like a key role in a minute. And here on the right, I show the population response to some step input current. In gray, we have a network activity of a microscopic simulation. I simulated 10,000 neurons of this particular type. And the exact solution is the solution of the refractory density equation here on top, colored in blue. So there's a perfect match between our integral equation and the microscopic network simulations. And what we see is that there's this particular ringing behavior, this oscillatory decay to a stationary state, that is an effect of neural refractoriness, and heuristic new firing rate models, heuristic neural field models, typically cannot explain such a ringing behavior simply because they are typically first order models that can only cover or capture exponential decay to an asynchronous state. What is more, and this is sort of very, very recent work that just got accepted in Physical Review E, but please also see the archived version of our work. We found a very, very surprising, very simple relationship between, or for our refractory density equation, namely that the eigenvalues of the refractory density operator of this operator L can be shown or can be obtained from this eigenvalue formula. So P is the ISI density. We take the Laplace transform, and the eigenvalues of our refractory density operator give us just the so the eigenvalues lambda n are, say, the roots of 1 minus the Laplace transform of the ISI density. So in fact, I want to repeat that and highlight that this is like a very general relationship that kind of comes up like automatically from our theory, that links basic spiking properties, namely the ISI density of our neurons, with the dynamic properties of the population activity, which are given by the eigenvalues of the mean field dynamics governed by the integral equation. But we can also go like one step even further. So if we plot these eigenvalues, then we see there's like a 0 eigenvalue that corresponds always to the asynchronous or stationary activity, but we find a spectral gap between the zero eigenvalue and the first pair of complex conjugate eigenvalues. And this spectral gap allows an eigenfunction expansion that can be very, very similar in nature to what has been achieved for the Fokker-Planck equation. So here's a list of references where an eigenfunction expansion has been used to derive firing rate models using this Fokker-Planck equation. And here we do like the same, do it like very, very similarly, but to the refractory density equation. I want to mention that our approach is basically, well, it includes the Fokker-Planck formalism because integrated fire neurons are but one type of renewal type spiking neurons. But our approach also goes beyond this, goes beyond the Fokker-Planck formalism, as it allows like more general renewal type spiking neuron models. And it has, on top of that, some further advantages. We'll come to that later, that we can extend the theory to like finite size fluctuations. But we can also explicitly write down, and in a very compact form, how we get firing rate models in a very systematic way. So this is shown here in the box. Interestingly, again, which is sort of common to like these systematic firing rate or reduced firing rate models, is that our activity A is, well, the backbone of our activity is the steady state transfer function F naught. And then we have some contributions of higher modes AN, and these modes AN, they have dynamics that are determined by the eigenvalues lambda n, plus there is some interaction between these modes that can add up on top of that. And to show you how powerful already the first order firing rate model is, so we only keep the first mode. Here I plot again this population response to a step input current for the Poisson neurons with absolute refractoriness, and already the first mode captures these transient dynamics to great extent. So that is very impressive. So this goes really beyond heuristic firing rate models, and we can also investigate the response to modulatory input. Here I plot the linear response. We can calculate it. So the zeroth order approximation is basically heuristic firing rate models. And well, these heuristic firing rate models, this black line in here, that cannot capture any resonance effects, but our first order approximation, our first order firing rate model really accurately reproduces the first resonance peak. So this is quite impressive. So far, we have put forward like the theory for a single population and highlighted how low dimensional dynamics can be explained with this in this framework. Now let's move to our neural field. So this is the general equations that we had before, just one population. We can go from one population to multiple populations simply by adding this population index alpha. Alpha goes from 1 to m. And we also have like this interaction between populations here and this membrane potential dynamics. And now next step is to allow for finite size theory. So here we go. We follow basically the theory that has been put forward by Thilo Schwalger, Deger, and Gerstner in this work published 2017, plus computational biology, where we actually replace the activity, or where we look at the true activity that is given as the expected activity plus some fluctuations. This psi alpha is some population specific Gaussian white noise that scales, or whose strength scales proportionally to the square root of the expected activity A bar divided by the number of neurons of that population, n alpha. And then we also have like this correction function here in the expected activity A. Okay. We still have to take like a continuum limit. So look at this cartoon here on the top left. So imagine this is basically here our population alpha, this is our population beta. They interact via the spatial, say, function or coupling function W. Typically, the population is in a spatial bin of size delta x, and we can also ascribe, or we can also define the number of neurons within each population by the neuron density n, small n times the size of delta. Okay, and now we take the spatial continuum limit, as shown here on the right. We take delta x to 0 and have to perform some steps to rush quickly through these equations. So what happened, like starting from our multiple populations model here, is here we have like our u alpha that depend on tau and t. If we take the spatial continuum limit, we have an additional dependence on the spatial location x, and our sum, our discrete sum, becomes now an integral with this coupling kernel w. Our expected activity now is also a function of x and t. What is important now is the true activity here. Here we find that the noise term now becomes a Gaussian wide, a wide Gaussian random field. So that is wide both in time and in space. And we also have like some seemingly multiplicative character of that noise. And yeah, finally, we also have the refractory density equation in these, also in this spatial variable x. Okay, what we want to do now is, like, we have here in the red part, in this true activity, in this finite size extension, we have this sort of multiplicative character, but actually this A goes into this kernel here. So we can kind of combine these red parts. I'll do this here. And we end up with a detailed neural field model in this box, where we have some noise term, some effective noise term eta, and this effective noise term eta that integrates this Gaussian random field with the via the coupling kernel, and then also weighted by the square root of the expected activity A. So this detailed neural field model, so this spatial continuum limit, has a great advantage, or basically it has like two advantages. So one is that by construction, the dynamics are consistent with the single neuron dynamics. And second, we can apply this battery of mathematical tools put forward by Kilpatrick, Ermentrout, Breslov, and co-workers to really study finite size fluctuations. And just as a side, we can also apply the spectral decomposition again to our refractory density equation and obtain like a low dimensional stochastic neural field model. Okay, and the very last slides, I want to quickly show how we can really treat finite size fluctuations. So here, as an example, we take a homogeneous ring network of a finite number of Poisson neurons that are evenly spread across the ring, and these Poisson neurons have absolute refractoriness. Here on the right, this is the sort of effective neural field model, and for realistic parameter values, we can get basically this bump activity. So this is like a stationary or like a stable bump that persists over time. The z-axis is the activity, the population activity, and one can really discern the multiplicative character of the noise. So at the center of the bump, there's large fluctuations, where at the flanks these noisy fluctuations, they decay more and more. Interestingly, we can have, when we look at the bump center and how it evolves over time, then this diffusive rendering of the bump crucially depends on the network size. So for large networks, as large as like 10,000 neurons, the bump remains almost constant, while for small network sizes of like, say, 1,000 neurons around that ring, this bump shows like more fluctuating of diffusive activity. So again, we could like extract these bump centers via the PVA and plot the activity. And I just want to remind you of what we had before. So this was the picture that Albert Comte and colleagues had like 20 years ago in their spiking neural network model, very detailed. And if we do like the same with our model, then we get a strikingly similar picture that is which is surprising in a way that we get for this sort of simple Poisson neuron with absolute refractoriness, a very good qualitative fit. Okay, and just to show you that our model can do even more. So if we look at the variance in these three cases, so again, small population strength have like a larger diffusion, and large populations here in yellow have like a very weak diffusion. We can even compute, we can calculate this effective diffusion constant analytically, and it depends, well, it scales with 1 over n, with 1 over the network size, and it also depends on the refractory time tau ref. So to come to an end, I've shown you in the first part how we can investigate and study low-dimensional population dynamics in this refractory density framework. The second part I showed you how we can use like a finite size theory of these refractory density framework to obtain a detailed stochastic neural field model. And as an outlook, I just want to mention that we can combine these 2 points to obtain really like a low-dimensional stochastic neural field model that captures the true dynamics and also finite size populations in our network model. So thanks very much and looking forward to your questions.
Great, thanks very much, Bastian, for a very enjoyable talk. So we have a question here from Valentin Schmutz, who says, "Hi Bastian, can the spectral decomposition method be applied to population equations corresponding to non-renewal neurons, or is it the renewal assumption that's necessary?"
Thanks very much for that question. So in general, one can, well, the theory is only valid for renewal type neurons, but one can use also like a quasi-renewal approximation to extend that network, also to allow for adaptation, for short time plasticity. And these are ideas that we have to develop this theory further on. So just to repeat, so as it is now, it properly works for renewal type spiking models, but we conjecture, or we're optimistic that we can also extend it to non-renewal type spiking neurons.
Okay, great. I actually had a quick question on the coupling functions that you were using. Are you just assuming exponential decay with distance, or is it some other form of coupling function?
We basically used a cosine coupling function.
Okay, sorry, I think I missed that.
So at least in the example at the very end. Of course, this can be very general. Here in this example of Poisson neurons with absolute refractoriness, we have like a cosine function, like a Mexican head, to mimic an effective, say, two-dimensional neural field of excitatory and inhibitory neurons. But in general, also this framework can be extended to allow for, say, really two different types of neurons that are excitatory and inhibitory.
Okay, great.